Is it already streaming live? Is it?
Yes, sir.
Oh, great. Very good. I'm not getting any. Oh,
Mohan or Swagata, can you check? Is it live now? It is showing here live.
It is a pleasure to extend a warm welcome to all the participants to this webinar.
Swagata, it is live, right? Swagata, can you hear
We're
me?
just checking.
Yeah.
Yes, I'm checking now.
Yeah.
it looks like it is live.
It should live, but somehow it is not coming to me.
Yeah, I can see all the photos. I can see.
Is it? Okay.
So we can start.
Yeah.
Yes, it is perfect. It is perfect.
Yeah, very good day to one and all. So we are going to have today the fourth lecture of Open Classroom Online Lecture Series in Atmospheric and Climate Sciences, jointly organized by South Asian Meteorological Association and SRM-IST. So without any further delay, so I hand over the session to Professor Someshwar Das to welcome the participants as well as the panelists. Over to you, sir.
Okay, thank you, Dr. Lakshmi Kumar. AVM Professor Ajit Tyagi, President of SAMA, Dr. M. Venkat Raman, Head of the Aerosols, Radiations and Nuclear Gas Group at National Atmospheric Research Lab, Tirupati, India.
Sir, Venkat Ratnam.
Venkat Ratnam. Venkat Ratnam. Thank you. Okay, Dr. Sarath Premlal, Former Director General of Meteorology, Sri Lanka Meteorological Department, and member of Advisory Panel of SAMA, members of the Advisory Panel of the Lecture Series, members of the Organizing Committee, distinguished participants, ladies and gentlemen. We welcome you on behalf of the South Asian Meteorological Association and SRM Institute of Science and Technology, Chennai, India. As you know, this is the fourth lecture on a very important topic on emerging techniques in atmospheric observations by a senior scientist from NARL, India. The entire lecture series is designed for capacity building of people in the field of atmospheric, weather and climate sciences by SAMA and SRM-IST. As you know, we have a distinguished panel of very senior professors and scientists from reputed institutions of this region who are experts in the fields. They will deliver lectures on fundamentals of the subject. The lecture series is targeted to postgraduate students and professionals of non-meteorological background who are interested in learning the subject of weather and climate sciences for research and operations. As you know, it consists of 4 orientation lectures and 12 lectures on atmospheric physics. This lecture series will continue for 4 months. Certificates will be given to the participants who are registered for the course and will complete the entire course with at least 75% attendance and successful performance of evaluation test at the end of the course. The lectures are live streamed on YouTube channel of SAMA. They will also be available afterwards on YouTube for those who could not attend the lectures live. We shall try to have more interactions between the speakers and the participants in this lecture series. Please write your questions in the chat box. Our moderators will pick up the questions at the end of the lecture and they will be answered by the speaker. So enjoy the lecture and we wish you all the best. Thank you. Over to you, Lakshmi.
Thank you, Professor Someshwar Das. So now I request President, South Asian Meteorological Association, Professor AVM Professor Ajit Tyagi, to talk a few words about the relevance of the today's topic. Over to you, sir.
Thank you, Lakshmi, and thanks Somesh for introducing the series of lectures which are being organized by SAMA and SRM-IST. This is the 4th lecture on a very important topic of observations part, the emerging technologies. As all of us know that observations formed the basis of atmospheric sciences right from the ancient times, where empirically, people used to observe the weather, especially the local weather, and they used to forecast the weather on the short time scales. But not only that, ancient times, all the civilizations, Indus, Babylon, Greek, Egypt, they had a good understanding of the processes also of, related to weather and climate, seasons, the sun's importance in the weather cycle. So all these rainfall processes, cloud formation. And as far as the observations were concerned, the rudimentary observations were taken even in the earlier period, like there's a mention of Kautilya at his time. Rain gauges were put in front of all revenue offices, and all the taxes were levied depending on the rainfall amount. But the real observations, the instrumented observations, started from 18th century with the invention of barometer and thermometer, and thereafter telegraph made the
Professor Ajit Tyagi, sir, you are unmuted.
Sir, you are muted. Tyagi sir, please unmute. Tyagi sir.
त्यागी साहब आपका अनम्यूट है, you're unmute, mute है rather. You can't hear. त्यागी साहब आपका
affecting the severe weather, and 1960s the Tyros made a significant breakthrough.
Again muted. Is there any problem from our side? Sir, you are mute.
Tyagi sir.
Maybe he is talking
I
through
think
mobile. That is why it is disconnecting.
Maybe.
Yeah. Yeah, you just leave it, sir. That is.
त्यागी साहब आपका फोन म्यूट हो गया है, माइक म्यूट है. You're not hearing us.
Number of observations form a
Okay.
very important
Sir,
go through.
आप म्यूट हो रहा है most probably.
बीच में म्यूट हो रहा है.
Maybe somebody, I am also on mobile, so could be.
Yeah.
Sorry. So now we have a good set
Again mute. Again mute.
as well as in the forecasting. So that is very important part. And what is really heartening is to see that new and new technologies are coming in remote sensing, which is providing high resolution data and variety of parameters, right from atmospheric chemistry, physics, radiation, test gases. And today's our eminent speaker, Dr. Venkat Ratnam, is going to talk about these technologies. He is head of atmospheric radiation and trace gases group at National Atmospheric Research Laboratory. Also, we have special comments by Dr. Premalal, who was former Director General of Sri Lankan Meteorological Department. Also, we are graced by the presence of Professor Bhaskar Rao, a member of advisory panel, and also I think our education committee also, he is the very active supporter and provides us guidance. So we are thankful to him also. And of course, all members of the executive support team who had been working at organizing committee to make these lecture series a success. We have now 250 participants already joining this, and many more I think will cross more than 300 marks. And I understand this registration have taken for this lecture up to 1800. So we'll be able to reach through our YouTube and the presentations which we share with all our registered participants to 1800 participants from the 40 countries. So in a way, this small step which we had taken by this lecture series, I think it is going in a big way in capacity building for the students, especially who are not from the meteorological background, but they are from the allied subjects, to give them a holistic view of meteorology, atmospheric sciences, climate sciences. So with this, my opening remarks, once again, thanks to Dr. Ratnam, Venkat Ratnam, to have agreed to deliver this talk.
Thank you, sir. Thank you, Tyagi, sir. Now I request Dr. Premlal, a former Director General of Meteorology, Sri Lanka, to speak, to give his remarks on this lecture series as well as on today's lecture. Over to you, sir.
Yeah, thank you. And good afternoon. Good evening. So Dr. Tyagi, Dr. Venkat, Ratnam, Dr. Somesh and other lecturers, officers and participants. So good evening to you. So today actually I'm going to focus my presentation, not presentation, the talk for atmospheric observation required for weather and climate prediction. So Dr. Tyagi also mentioned that the history about the climate observation in the world. So in the world, actually, climate observation started in mid of 18th centuries with the basic data, so probably rainfall data. So even Sri Lanka started the data observation in 1961 with the basic rain gauge network during British era. So I think India also started the same similar period because you know that all our countries are under the British colony. So we all started doing that at the same time. So gradually the observation network, the developed, and now many atmospheric data observed in the huge network with many atmospheric parameters. So I just on that I'll focus, you know, that we look at why these observations are necessary for weather prediction. So before that, I would like to pay your attention as well as my attention for the indigenous knowledge. So we, the ancient people have. So sometimes, you know, that the young people does not know. So we had some, you know, that indigenous knowledge to predict weather. Actually, they had a good knowledge for weather prediction, just looking at the environment without any digital data and without any analysis. But now we are actually predicting predicting weather by, you know, that using computers, observation data and others. But earlier they did not have such facilities. But even that, actually they should have, they had, you know, that good, I mean that they predicted, you know, that the weather very accurately. So the reason is that they were highly attached to the environment. So not like now. Now actually most of we are highly focused for computers and high tech, and even for the mobile. So we do not have much understand about the environmental changes. So now we cannot, you know, that predict weather by just looking at the environment. So actually this is just example. By looking at the atmosphere, they understand the atmospheric pattern. So not the data, actually, they just understand, you know, that so what are the patterns, you know, that annual pattern, you know, that like seasons. So they had good knowledge about that and correlate with the rainfall and temperature. So that is how, you know, that they just predict weather just looking at the environment. So not only that, most of the animal are highly sensitive, not only animal, even, you know, that some vegetation are highly sensitive to the atmospheric changes. So with their behavior, the people had knowledge to predict weather even without any observation. So now the scenario was is very different. From one side there's a climate change, right? So it is very difficult to predict the climate, and the other side the land use changes and changes of vegetation cover. So sometimes, you know, that some animals are vanishes. So those are the things actually. So we cannot rely on the atmosphere. So top of that, the people are not sensitive to the environment. So we have to rely with the observation data for weather prediction. So I remember when I joined to the Department of Meteorology. So we had only 22 synoptic stations, and we exchange data via WMO, global telecommunication system, that is GT system, at a very low rate. Sometimes, you know, the data received after 6 hours, and even local data exchange via telegrams and telephone. So it takes, you know, that one day to those one day and those data used for only climatic purposes. So the 2 times, you know, the satellite data we observed, satellite images we observed in the morning and in the afternoon. Only observed changes. So we can, you know, that get, you know, that those satellite images, the changes of clouds. So not other parameters like, you know, that temperatures and others. So by analyze those data manually, we provided weather forecast. Even there are many equations Now actually those equations are used for the numerical weather prediction. So it was not able to use manually, and we just followed the weather persistence. That yesterday weather, what was the yesterday weather, and the day before yesterday's weather. So with that, and that the climate observation, we just predict that what will be the next 12 hours weather. Not 7 days, so that not medium range and not seasonal weather prediction, just that. So we provided weather forecast just 1 or 2 days. Even that there was high demand for atmospheric data at high frequency. So technology was improved. The numerical weather prediction system were improved and very fast with the high-end servers or supercomputers. So now, the satellite technology started in 1970s. So now there is, that heavy, huge satellite network, that even India. So you observe, that satellite images, that very frequent, high frequency. So with, that very, maximum, with maximum data. So with that, computer analysis has been improved, and there is high demand for the weather forecast and climate service to address, especially address to extreme weather with the climate change. So now we are, we are frequently getting climate extreme, and now there is that high demand from the people for the especially extreme weather, not that the rainfall and temperature. So extreme weather is that very important, not only for the people, that even for the many sectors. So we need to go for seamless weather prediction, that is that now cast into the future weather prediction. For that, it is much necessary to get that more observation data with high frequency. So observe atmospheric parameters will not address for this seamless weather forecast. We need to improve numerical weather prediction globally, nationally, and locally, that is using limited area model. So for that, we need high frequency data with huge network. For that, we need to go for automated weather observation system. So without automated weather observation system, it cannot be, cannot be predict that extreme weather situations. So even some countries still not interested. So some countries I know, even Sri Lankan people still not interested that for the automated weather observation system. But however, we have to go for that, go for the automated weather system. So that is the answer for data assimilation, especially for the limited area model. So I think COP27, which was held in last November, also focus their discussion for improve the climate service and enhance the observation network. So even some countries not run a limited area model, data itself can be used for understand the possibility of extreme weather. The focus in that, Sri Lanka Meteorological Department established rainfall observation network, that is that automated rain gauge network along the southwestern coastal area. So we are getting that more frequent climate extremes, especially that flood during southwest monsoon, onset of southwest monsoon, especially in May. So just targeting that, actually we established rain gauge network, that's 100 rain gauge network along the hello.
Yes, sir, we can hear you. Premalal sir, you are muted.
Okay.
Okay.
Finally, what I want to tell you, with the climate change, we experience extreme weather condition with high impact. For the adaptation, it is much essential to improve weather forecast. So dense observation network and high frequency observation data will help to improve weather forecast with the predictability of extreme weather and predict extreme climate event, not only near future, but also next few decades. Thank you very much.
So thank you, Dr. Premlal, for providing the remarks on this today's lecture series as well as today's lecture. And also a few words about this observations and other things. Thank you very much, sir. So now, without any further delay, I request Dr. Rohini to introduce today's speaker, Dr. M. Venkat Ratnam. Rohini, can I share the slide or you will share the slide?
Yes, Dr. Lakshmi Kumar, if you can share.
Yeah, yes, please.
Right now,
Hello. Yeah. So good afternoon, all. I am very happy and delighted to introduce today's speaker, Dr. Venkat Ratnam. He's scientist and head ARTG National Atmospheric Research Laboratory, that is NARL. After joining as scientist at NARL, he's carrying out research in frontline areas of atmospheric sciences. Prior to his assignment as scientist in NARL, he worked as postdoctoral fellow and visiting scientist at Taiwan, Germany, and Japan from the years 2001 to 6. And right now he's leading the ARTG, that is the Aerosol Radiation and Trace Gases Group. His major interests are middle atmospheric structure and dynamics, aerosol, radiation and trace gases, long-term trends and climate change. He has generated several experimental campaigns in collaboration with national and international institutes, including NASA, to address several issues related to atmospheric science. He has published more than 230 research papers in highly reputed international journals. 15 students were awarded PhD degrees under his research supervision. In recognition of his outstanding scientific contributions, he has received several awards, including prestigious Japan Society for Promotion of Sciences Award, Best Paper Awards at national and international conferences or workshops, and NASI Scopus Young Scientist Award for the year 2010 in Earth Sciences. He became Fellow Andhra Pradesh Academy of Sciences. He is a life member of several prestigious societies like IMS, IETE, ISCA, etc. He is member of several high-level scientific and technical committees at national and international levels. He has also been appointed as scientific discipline representative from India for International SASCO-10. Very recently, he has received India's prestigious Shanti Swarup Bhatnagar Prize for 2018 under Earth, Atmosphere, Ocean and Planetary Sciences from Honorable Prime Minister of India. He became advisory committee member of the Vienna Convention Trust Fund for Research and Systematic Observation of United Nations Environment Program Ozone Secretary. Recently, he authored a textbook on terrestrial atmosphere and ionosphere, physics and experimental techniques, jointly with Professor V.V. Krishnamurthy, which is very useful for postgraduate, graduate, and research scholars, and even early career scientists. With more than 25 years of academic research and administrative experience, blended with progressive views, organizational strength, he is contributing to the growing ambitions of Department of Space. So we welcome you, sir, today for your talk. Over to you, Dr. Lakshmi.
Thank you, Dr. Rohini. Sir Ratnam, sir, now the floor is yours. Please share your presentation.
Is it my slides are okay?
Yes, sir, fine.
My slides are moving?
Now you please move them.
No. Wait. Is it okay?
No, you have to keep in full screen. Full view, yeah. Now you try to move the slides.
No, they are not moving. One second.
So meanwhile, you can send me PPT otherwise.
1 second.
Yeah. Yeah. You move the slides, sir. Yeah, fine. It is fine now. Yes. Please go ahead. You are muted. Please unmute.
First of all, thank you, Dr. Rohini, for nicely introducing me to the participants. Respected Professor Ajit Tyagi, President, SAMA, Professor Someshwar Das, Secretary, SAMA, and my dear other panelists from SAMA, particularly Dr. Lakshmi Kumar, and my dear participants from various parts of Asian regions. A very good afternoon. And you all know that this is the 4th in series of SAMA-SRM IST lecture series, and hope you have all enjoyed and enriched with the last 3 lectures by Professor U.C. Mehanti and the second one by Professor Ajit Tyagi and Professor S.K. Das. Today I'll be talking on the emerging techniques in the atmospheric probing. Before I start, I must say that this is a very vast subject, and in a time period of an hour or so, it is very difficult to cover the complete gamut of the technologies available for atmospheric probing. But I will try to convey a few of them. Though I'll be emphasizing on new techniques, but before that I must convey or cover existing or well-established techniques. And I assume that most of you are from the, you know, the basics of the atmospheric science and from masters or early career PhDs and research scholars. And my work has been a little reduced by my previous speakers. However, I'll not be touching about anything about the today's observations which are required for the operational forecasting. But I'll be touching upon the techniques which are almost like a completely new for the research and to some extent to operational forecasting. So in the next few minutes, I'll be covering on first, I will be briefly introducing the Earth's atmosphere and its environment, and the basic atmospheric parameters which we need to understand for the understanding the which we need to know for understanding the atmosphere process, and different techniques and platforms available for atmospheric probing. It includes the surface, in situ observations, and radio and optical observations. And mostly, I will be covering of the new techniques available in the in situ area. And to some extent, I'll be covering about the physical mechanisms behind the measurements, and finally the summary. And we all know that there are the 3 realms of the Earth. One is lithosphere, the solid part of the Earth, the hydrosphere, the liquid part, and the gaseous envelope, that is atmosphere. And all the 3 realms are together tied to the called as biosphere. And the sun is ultimate energy for all these spheres. And it includes the electromagnetic radiations from which are having a wide variety of radiation that includes from hard X-rays to the very soft rays. And while transmitting these electromagnetic radiation from the sun to the Earth, many of these electromagnetic radiation will be filtered at different layers of the atmosphere. And for example, the hard X-rays will get filtered in the upper part of the atmosphere, and the UV radiation will be filtered in stratosphere due to presence of ozone, and some part of the electromagnetic will reach the Earth's surface. And this in turn will generate several atmospheric processes, which will have the part of the boundary layer, including the free troposphere, and also the upper layers. This we call top-down mechanism. And in turn, once the solar radiation is reached absorbed by the Earth, it will radiate in different radiation, and those will be affected again from different layers of the atmosphere. This is called from bottom-up approach. So to understand several atmospheric processes, we need to have different wide varieties of instrument, because no single instrument will provide the information which we require at all the spheres of this atmosphere. And for probing this one, several techniques has been invented that includes the surface observations like in situ and radar and optical, and including the rocket and several. But these are the point observations at a given time, at a given place. We'll be able to measure, we'll be able to know the atmospheric processes, but these are not enough to cover the complete globe. So to cover the complete globe, some of the sensors has been kept in the satellites, where we can get the information throughout the globe. So this is the free filter, and to some extent, some of the earlier, Professor Ajit Tyagi was mentioning that 18th century that observation started, but to know that almost like 1,000 to 2,000 years before, the atmosphere, if you want to know that atmosphere, how it was behaved, people used to use the paleoclimate by cutting the 3 rings from the zone, how the ring is established in a given year. So people will be coming to know what is the weather and climate prevailing during those times. But now we will talk only on the atmospheric observations covering right from surface, mostly covering from the troposphere, but to some extent I'll be covering from the middle and upper atmosphere. And we all know that the basic atmospheric parameters, mostly that meteorological parameters includes the air temperature, and people want to know that how much temperature, summer, how much is the hotness of the summer, or winter, how much it is cold, and also the pressure. This parameter is very, very important, particularly during disturbed wind conditions. We'll be knowing that there is a low pressure system being developed at Arabian Sea, or Indian Ocean, or Bay of Bengal. So at that time, the pressure becomes very important parameter. And water vapor and variability, the amount of water vapor present in the atmosphere is also very important parameter, which one has to be measured very accurately. And also wind speed and wind direction in general. And cloud type and distribution also very important to know. And the type and amount of rainfall is nowadays more concerned about this parameter. And to some extent, sunshine hours is also another meteorological parameter, but it's not so important in the tropical latitudes. But the sunshine hours also become very important if you go to mid and polar latitudes. And in today's talk, I'll be talking about some of these, how to measure these things and what are the advances made in measuring these meteorological parameters. And to some extent, that air quality and air pollution has become very, very important in the changing climate, and how the aerosols particularly being measured using the optical or in situ measurements I'll be covering. And I'll not touch upon anything about radiation or trace gases in this thing, except that water vapor or ozone. And of course, visibility has also become a very important parameter, but I'll not be touching in this one. Now, how do we want to measure them? So we want to measure these meteorological parameters as many locations as possible, both vertically and horizontally. Vertically means from the surface to the top of the atmosphere, and horizontal means both latitudinal and longitudinally. And we want to measure these meteorological parameters as continuously as possible. People may prefer having every minute data also some of these parameters during disturbed weather conditions, but in general, hourly measurements are very good of all these meteorological parameters. And we want to measure them as long as possible to understand the whether we will be knowing, we'll be measuring in the instance and time of instant weather. And if you want to know the climate, the average of more than 3 decades of this data will become a climate. But we need to measure all these things. We need a cheaper and most accurate and uninterrupted data sets of all these things. And then how to get these things. So before that, there are several atmospheric processes, both having the vertically and also horizontally. For example, as I mentioned in my introduction slide, the sun is the ultimate source of energy. And this will produce the several tropospheric disturbance like eastward propagating cloud convective systems. And these convective systems will generate wide variety of waves, which will propagate to the higher altitudes. While propagating, they carry energy and momentum along with that, and they disturb the layers present in above the in the stratosphere or mesosphere or even in the upper atmosphere. So this is the one part of the region which we are interested. And another is that there are several constants present in the atmosphere that includes aerosols, that PM1, PM2.5, PM10, all these, and several and trace gases are also very, very important to monitor. This comes under the second part of the Earth's atmosphere, which will be very, very important. And there are some nowadays the weather and climate, it does not restrict to the troposphere or lower part of the atmosphere, and it has been recognized that most the climate signal particularly will be known very clearly in the middle and upper atmosphere, because any small change at the surface, it is equal to translating to the 10 times or multiple times that same parameter will be picked up in the middle and upper atmosphere. So it becomes very easy to see the climate change signals in middle and upper atmosphere. So this is also become a very important, and those middle atmosphere process, whatever picked up because of lower atmosphere process, in turn they will pick up the lower atmosphere. So now it has become very important to study the coupling from both lower to upper and upper to the lower atmosphere. So these are some of the aspects which we want to know at a given place. But suppose if you want to know what is happening, it is not it is enough to know what is happening at a given place, but we want to know it at other places also. For example, the sun is not, means that radiation which received from the sun is not uniformly distributed across the globe. It is highest over the equator, and if you move away from the equator, it will be less. As a result, we will be having a imbalance between the equatorial and polar latitudes. It will generate a large-scale circulation features, and this in this process, an air is being transferred between the equator and polar latitudes by the several circulation And the best known circulation feature is the brew adsorption circulation, where air from the tropical latitudes will be transported to the mid and polar latitudes. And the best example of this one is, we know that ozone is because of equatorial high solar radiation, most of the ozone will be produced over the equatorial latitudes. But at a given instant of time, more ozone we can see over the polar latitude. This is mainly because of the presence of brew adsorption circulation, which take the air from the equatorial latitudes and put it in the polar latitudes. So to understand all this process, we need a wide variety of measurements, and at a single point is not enough. So we need to know the global, the process happening at the global scale, and to how to probe these atmosphere. And there are several instruments, as my previous speakers have also already introduced in the previous lectures. And most of them are covered with the surface. And now I'll be touching more upon the in situ observations. And the surface is only just below the boundary layer, what is happening that we'll be knowing. But if you want to know the process happening in the free troposphere, we need to go for the in situ observations or optical radar. And if this instrument, all these instruments in this slide, you can see the approximate altitude coverage by these instruments. And in this talk, I'll be talking about below 100 kilometers, the emerging techniques for probing in both in the in situ, surface, and optical and radar fields. And to cover the higher altitudes, we need to depend upon either in the rocket or in the satellite observations, which I will not be covering in this presentation. Now, coming to first, I will be talking about surface observations. And these are all, we all know that you might have seen whenever there is a disturbed weather condition, that news in the news channels, so people will be showing that anemometer or wind vane, that the vane which is rotating. Then, so these are all nothing but this will measure the wind speed and wind direction. And cup anemometer is widely used for the measuring the wind speed. That is how it produces that pressure difference produce force on the cups, and that will rotate proportional to the wind speed. And for getting the wind information, we will be using the wind vane, and the vane will align in the airflow direction. And sonic anemometer is widely used for the wind velocity measurements. And this basic principle is the sound velocity will be used to determine the instantaneous wind speed by measuring how much sound waves travel between the plane of transit. And here, all the three wind components, that is zonal, meridional, vertical, I mean east, west, or north, south, or vertical component, will get from these measurements. And there is another hot wave anemometer exists for the wind velocity. And this is basically energy loss of heated wire through instantaneous flow velocity from electric voltage measurements. This is the basic principle for measuring the wind velocity in the hot wave anemometer. And to get the temperature, we'll be widely using the resistance thermometer or thermistor or thermistor. This basically depends on temperature on electrical resistance or platinum or nickel. And to get the humidity measurements, we'll be using either air capacity or absorption dew point hygrometer or psychrometer. And this is basically the temperature difference between two ventilated thermometers will be converted. One will be covered with a wet wick, and this gives wet bulb temperature, and the difference between these two will give the relative humidity. And to know the water, the amount of rainfall, we widely use the rain gauge, amount of rain collected in a given time at a given place. This is used. And when you are traveling in the aircraft, you might be seeing that there is one flag will be there, which will it will be indicating the pilot how much which direction the wind is flowing, and how much the wind is, depending upon whether it is how much it is being inclined. So all these are all basically used for the surface measurements, and these are all very accurate and very high temperature we can get this information. But note that these are all at a point observation, and that too restricted to the surface of the Earth's atmosphere. In order to get some of these parameters, like temperature, water vapor, relativity, or wind speed, wind direction, we need to go for the different techniques that we called as in situ, that is the radio sonde techniques. So this radio sonde, some of these sensors will be tied to the balloon and will filled with hydrogen or helium gas. And while traveling, because of being the lighter gas, it will try to float in the atmosphere, and while traveling, it will give this at each second or at a given response time of the sensor, we'll be getting all these temperature, wind speed, wind direction, and wind speed, wind direction, relativity, and temperature measurements. And this is one of the.
Ratnam sir, sorry to disturb you. Some participants are asking to show with the pointer.
1 second.
Yeah, please.
Okay, is it okay now?
Yeah, you can use a pointer.
Yes.
So that
Yeah, yes, sir.
yeah, fine. Okay, sir.
Oh, it's not possible. I'm not getting those. Okay, fine. Is it okay now?
Yes.
Okay.
Yeah.
Okay. And these institute measurements are, in fact, almost like more than 100 years back. It has been used for the first time in 1920s. The upper air soundings have become very popular. And since then, several advances has been happening in this area. But today, still, this remain as a very important instrument for getting the meteorological parameters, particularly the upper air measurements. And basically, we will get the temperature using the thermistor base. And it is a bimetal sensors and thermocouples with a coating. That coating is mainly because to isolate the direct radiation interaction from the sun while it is floating. And basically, this temperature will be measured based upon the resistance. And resistance is directly proportional temperature, we all know from the Ohm's law. And the temperature will be known from this simple equation. And coming to the relative humidity, we'll be mainly using the carbon hygroscope or thin film sensors. And basically here we'll be measuring the capacitance, and the capacitance is directly proportional to relative humidity with the equation shown here, where the capacitance is directly proportional to area of the plates and the thickness of the dielectric thing. And coming to the pressure, we will be using the Barometric pressure sensors. This is basically the capacitive transducer plates, which are separated by the two rods. One is with the very tight, and another is the flexible membrane. And any change in the pressure will try to oscillate this membrane, and that will give directly measurement of pressure. But nowadays, that institute measurements are not using the pressure sensor, rather than they're deriving using the hydrostatic equation, because the pressure the temperature is known with a very high accurate, and the position is also known. But we've known the position and temperature, will get the pressure using the hydrostatic equation. And wind speed and wind direction, earlier we used to have from the Raven sounder, that is the radar used to probe the metallic strip tied to the balloon. But nowadays, after the GPS satellites from the US has become very popular to know the exact positioning. So using that technique, we'll be getting the wind speed and wind direction. And the wind speed is that the flow of the balloon with respect to at a given place. Then how much fast it is going, that will give the wind speed, and which direction it is going, it is the wind speed. And we can from the known wind speed wind direction, we can get the zonal wind and major wind from the equations given here. So no need to worry too much, because but only thing is that these institute measurements are used to get the meteorological parameters that cover temperature, relative humidity, including pressure, and wind speed and wind direction. And in this slide, I'm showing the typical radio sonde launch rate from our station Gadanki. You can see that the temperature profile here, covering from surface to 35 kilometers, that is the balloon burst altitude. And you can see the tropopause is very nicely marked around the 17.5 kilometer. And you'll get the relative humidity like this, and wind speed in direction on 1st January 2008 at 12 UTC. And such institute measurements are available across the globe. Almost like 200 stations are there, but among them 800 stations are regularly operating even today. And these are very crucial for the weather forecasting. It has become very crucial input for the weather forecasters. And but one important thing is that the relative humidity or water vapor content above 12 kilometers or minus 40 degrees centigrade, these radio sondes are not accurate enough. And to get the accurate measurements of water vapor, and it's very important. In fact, this water vapor entering into the lower stratosphere plays an important role in the chemistry of ozone, whether it's destruction or whatever that oxidation we call with the ozone related thing. So it is very important to know how to measure accurately this water vapor in the utilized region. But these normal radio sondes will not work under these low temperatures. So to know this water vapor very precisely in the utilized region particularly, the cryogenic frost point hygrometer has been invented, and this gives the profiles of water vapor in the utilized region. Basically, this is a chilled mirror principle used to we use the cryogenic liquid, which is able to cool the mirror to between 30 degrees to 100 degrees below any ambient frost temperature. When the air flows from this thing, this operates a small mirror at a precise temperature. You can see that my pointer here, and this will generate a thin constant layer of condenser mirror. And the LED light that is reflected off the mirror, and the photo detector sends this reflected light, which varies with the amount of frost that is coated on this film. And the photo detector is then used to adjust the mirror temperature, and this mirror is constantly heated or cooled with the cryogenic liquid. And this mechanism will allow the mirror to get heated and cooled quickly, so that temperature reflects the current frost or dew point. A typical profile which is measured by SPL group over Hyderabad is shown here. You can see the temperature on the 3 different days in 14 June, where it is measured the amount of water vapor in the utilization. These are very, very high precise measurements, and these are all almost like a new emergent technique for the utilized region water vapor profile. And this is the last panel is measured relative humidity over the ice. You can see how much variation is there, and this is very going to play important role in the lower stratospheric chemistry. But now, if you want to know, these are all only the meteorological parameters until now I covered. But if you want to know the trace gas, particularly the ozone, we need to depend upon the ozone sonde, and there are quite different types of ozone sondes are available. And here we shown in this one is the ECC, that electrochemical cell ozone sonde. And basically, this will have the two solutions separated by cathode and anode solution. And this is one cathode solution will that only difference between the anode solution is that it will be more concentration of potassium iodide in the anode solution. So the basic equation how the ozone be measured is that the potassium iodide, when it passes through the ozone, or when it is interact with the ozone, we'll get in the iodine. When iodine is converted into iodide, it release the 2 electrons, and this is the measure. This is what we measure for measuring the ozone. So this simple equation gives the difference between the major sensor output current and the background sensor background current, and this sensor background current will measure at the surface before launching the sonde. So the difference between these two gives that amount of ozone being measured at the given altitude. So when this tied to the balloon, and it will goes on gives the ozone profile right from surface to the balloon burst altitude, and this is the basic principle which use, and this typically weight from 600 to 700 grams. So it will be easily to carry it in the balloons. So the basic profile, a typical profile, again launched from our Gadanki, is shown in this black color line. This ozone sonde launched on 1st October 2014, and we have simultaneously we have a reverse spectrophotometer which measures the ozone using Umker method, which gives sunrise and sunset occultation. During that time, we'll get the profile of ozone. But this is a smoothed one. But the advantage of ozone sonde, you can see that there is a huge variation, particularly in the troposphere. We all know that tropospheric ozone is bad for us, and the stratospheric ozone is good for us, because this will protect the UV rays reaching to their surface at the stratospheric altitude. But if it is more ozone in the troposphere, it is very harmful. Particularly, it has an impact on even in agriculture and on our health. So, but to precisely understand this one, we nowadays we depend upon these ozone sondes. However, there are some optical instrument has come, that is what we call the dial, differential absorption lidar. I will be touching in later slide about this one. So this is basically to get the ozone profile will depend upon the ozone sondes. Now, there is another new emerging technique I can say, that to get the profiles of aerosol and clouds. So far I covered the meteorological parameters, but now the people want to know the profiles of aerosol and cloud, because this has become very important parameters for the understanding global warming and climate change. So, and remotely we can measure the clouds and aerosol, but now all the properties of the aerosol clouds is not possible remotely, which I will be touching upon when the optical instruments I'll be covering. But here I'll be introducing this compact optical backscatter and aerosol detector, popularly called as Cobalt. So this gives the profile of aerosol and cloud, and it has basically will have two LEDs operating at blue and red channel, 455 nanometer and 940 nanometer. And when the backscatter ratio, two wavelengths will be measuring, and we also measure the color index, which is the ratio between backscatter at 940 nanometer by the backscatter at 455. And if the color ratio is more than 7 and backscatter ratio at 940 is greater than 2, and the eye saturation, if it is greater than 70%, we treat those as aerosols, and otherwise we call as a cloud. A typical profile is shown here, where in the blue color, you can see the blue channel 459 blue channel backscatter ratio, and the red, the 940 nanometer is shown in the red color, and whereas the color ratio, it is shown in the cyan color, and the eye saturation is shown in the orange color. You can see that there is a very thick, the cloud layer is sitting between 13 to 15 kilometer altitude, but above this, all these conditions satisfy that color index is greater than 7, backscatter is greater than 2, and eye saturation greater than 70. And these are all called as aerosols present in the atmosphere. This is also almost like a new emergent technique for profiling the aerosol in climate, which was not possible earlier with the remote sensing instruments. Now, another one important sensor is the profile of the clouds. The cloud number constant, because there are some indirect methods, but the direct method for the institute is that a newly emerged technique is cloud particle sensor. This is first invented by Dr. Fujiwara from Japan. And now it has been commercialized those techniques, and we are several places this cloud particle sensor is being used, and this is basically is equipped with a diode laser at 790 nanometer and 2 silicon photo detectors, and you can see this the basic principle, and it's very difficult for me to cover in this one, but I'll be showing the references where you can get all the details in the last slide. So basically, this will detect the number concentration and the degree of polarization will give whether it is a spherical or non-spherical thing. So the number concentration of the cloud particle is very, very important for aerosol cloud interaction studies, and for fundamental understanding, these are all very, very important parameters, and these are all almost like a new emergent techniques, I can say, in the institute profiling. And typical example taken from the Ravikiran et al. Recently published in atmospheric measurement technique, you can see that number concentration at this utility region is a very high number concentration. Basically, these are coming from the cirrus cloud. And these are all newly emerged techniques, I can say. And there are coming to the different platforms. In fact, whatever the sensors I mentioned so far, they can be kept in different platforms to get the different ways of getting the different profiles, I can say, are different, how we can get all these measurements at different platforms. This slide is telling. So suppose if all those 5 institute measurements which I mentioned in the previous slide, if you tie to this a threaded balloon, which is tied to the ground and almost like 1 to 1.5 kilometer, and this has become very, very important nowadays for getting the, you can see because now that the air quality or air pollution studies have become very popular, and we want to know the amount of the pollution surface and at a given a little elevated altitude. So this is the threaded balloon for widely used, and all the sensor can tie to this one and can send it to up and down, and it can stay for almost like some 6 to 7 hours at the constant altitude, and we can get continuous measurement from that. And suppose if we tie these sondes to the balloon, radio sonde, which I mentioned in the previous slide, we can get up to the balloon burst altitude, and basically this can carry up to 5 kg payload and cover up to 35 to 45 kilometer. And suppose if you want to go to the higher altitudes, get the information from very, very high altitudes, the high altitude balloons are also which is shown here. And basically that Tata Institute of Fundamental Research in Hyderabad, it has this kind of all different varieties of balloon. And there is another type of called zero pressure balloon, and these are all which can carry very heavy payloads up to 400 kgs. And for basically for astronomy or atmospheric or engineering, for testing several of even satellite payloads before sending to the actual satellites or rocket payloads, these will be tested at this kind of balloons. And nowadays, in fact, very recently, that super pressure balloon concept has become very, very popular, and it can carry about 10 kgs. And basically, they will flow in the Utilis region, and we can get a global measurement. These are all, you can see recently that Kenneth French team has released these kind of super pressure balloons from Ascension Island, which is shown here. And in a days of from 60 to 90 days, it will cover complete globe at a fixed altitude, almost like 18 to 19 kilometer. And you can get, while it will transmit the whatever the observations to the ground station wherever the ground is coming. The way it has a recorder here, and all these are very, very precise measurements that people are using, getting from these kind of super pressure balloons. And there are some people also use the drop Sundays where particularly during extreme weather, to understand that one, and during the cyclone things, so they'll drop the drop Sundays to know the profile of the measurements in the disturbed weather condition where it is not possible in the normal way. So these, for coming to the advantage of all these techniques, they are very reliable and accurate. And even today, the ground truth for the new techniques of satellites, they are using for this kind of in-situ observations. And I must say that they are all-weather capability, but only limitation is very expensive and infrequent, and it's very difficult to, because so much of cost is involved. And as a process, these are all poor temporal resolution. But coming to the accuracy wise, these are all the best known even today. So these are coming to the for the institute, but these are all point observation, but we will not get the more information up to the balloon burst altitude only we can get, or at a desired altitude only we can get. But if you want to know the more details, we need to depend upon, there are some other techniques has come. For example, recently drones has been also utilized or used very frequently. And a typical example is shown here from the Gadanki. We are using this drone, and all these in-situ measurements which I mentioned previously, like radius sonde, ozone sonde, frost point hygrometer, cloud particle sensor, and cobalt, or microexperiment PM sensor, we tie to this kind of drones, and this can carry the payload of 3 kgs up to, and can go up to 3 kilometer altitude. And one of the Eclipse campaign we conducted in the recently, and you can see that the drone measured the PM parameters here. Up to the we almost gone to the 1.2 kilometer altitude, and now we are in the process of developing up to 3 kilometer altitude, which we can get, and these are all completely new. In fact, we do not lose any of these observations because it's those just go up and come down, and while going up and coming down, we can get this kind of profile, and it is very easy and cheaper, and there is no loss of the payload, and it has become very, very important nowadays. But these are all maximum limitation. The normal drones, the commercial level drones, can take even 100 kgs, but they cannot flow beyond 500 meters. But these are all the atmospheric drones, which we are interested to go even beyond 3 kilometers, or it should cross minimum boundary altitude to get more details on the air meteorological parameters, even aerosol or cloud parameters in this boundary level to understand the boundary process. But these are all not covered beyond 3 kilometers or 4 kilometers. But the very recently that IITM Pune has bought the UAV, it's an unmanned air vehicle, where we can use this kind of some of these in-situ measurements tied to this aircraft. And while we can probe, we can get the meteorological parameters or all these in-situ, whatever I mentioned in the previous slides. Using a very high temporal resolution, we can get it. But only thing is that these are all very, very costly, and it's not possible to operate very frequently. But for understanding the basic understanding or the complete understanding of the atmospheric process, these are playing very, very important role in recent days. These are almost like a newly emerged or emerging techniques for getting the information from the atmosphere. Now, all these things which I mentioned here are in situ. Either you take that surface observations or the in situ or upper air observations. This will go and sense the atmosphere and give the information. But it is not possible to go at every altitude and every place to get those information. So basically, we use the radio and optical techniques. And this slide shows the frequency and wavelength, which will be covered in the radar thing and the LiDAR. Basically, the frequencies are from high frequency to the L band will be using to get the information on the clear air motions in the atmosphere and information on convection, precipitation, and also on the ionospheric processes. And these are very widely used. Even it has become very popular in using this information in the weather forecasting models. And if you want to know some of the tiny particles suspended in the atmosphere, that aerosol clouds or trace gases or water vapor or temperature, we will be mostly depending upon the LiDARs. And there are some, if you want to know the cloud or precipitation information, or particularly during Doppler weather radars, the bands is used from SC, from K band are widely used for this one. So I'll be covering slightly among now in the radar and the LiDAR, and to some extent the other optical techniques available for the bilateral probing. Now coming to the radars, there are wide varieties of wind profiles or radars have emerged, and this is again during the Second World War onwards. These radars have become very popular for probing the atmosphere, and it has wide varieties depending upon the frequency or depending upon the altitude we are interested. Different kinds of radars are emerged. For example, L-band frequency that 1.3 gigahertz will get the information on all the three-dimensional winds, particularly from 0.3 to 5 kilometer, and it is almost continuous. 24/7 into 365 days we'll get using this wind profiler, and this provides very, very important information right from surface to almost 5 kilometer. Suppose if you want to go for the little higher altitudes up to 20-21 kilometers, we popularly use the MST radars called as mesostatic tropospheric radars, and basically these uses the 50 megahertz, and we'll get up to 20 kilometer altitude, and also from to 65 to 80 kilometer. So sometimes we'll get information from the mesospheric altitude also using these radars. And to cover higher altitudes, we mainly depend upon medium frequency or HF, high frequency or meteor radars. They typically operate from 2 megahertz to 50 megahertz or 30 megahertz, and they will give almost like continuous observations from 70 to 100 kilometers winds. And also that to some extent the meteor radars can get the information on temperature. And there are some other varieties of radars which I will not cover here. These are basically for the ionospheric research. Infrared scatter radars are being used, popularly used. And very popularly, we come across the Doppler weather radars or X-band cloud radars. And basically to get the clouds, information on cloud and precipitation, these radars have come. And some of these slides, the photos shown here are all from the Gadanki, our NARL site. And you can see the wide varieties of radars which we have at our site. Low Earth wind profiler 4x4. This is a portable wind profiler. We can take anywhere and get that information from there. And this is a fixed 16x16 wind profiler, and this is MST radar, and this is HF radar, and the cloud radar is shown here. So these are all systems are available and fully operational from the NARL Gadanki. And what it basically gives is basically this will sense the refractive index gradients. Any of these radars which is operating at frequency greater than 30 megahertz, they basically sense the refractive index gradients, and this refractive index gradients is directly proportional to the water vapor and the temperature in the troposphere and lower stratosphere, and the electronegativity gradients in the mesosphere or upper atmosphere. So this is the typical the probing is shown here. We will shoot the vertical and also half vertical east or west or north or south. A minimum 3 beams are required to get all the 3-dimensional winds, and that is east, west, or north, south, and vertical. And this is the only instrument where we will get the information on the vertical wind. And we all know that how much important the vertical wind plays in meteorological applications. And this is the only so far existing technique which will give direct measurement of vertical wind. So right from this near surface to the almost like 22 kilometer, we'll get one spectra like this, and each altitude will get this kind of spectra. Huge information is buried in the spectra, and the amount, the shift in the Doppler frequency will give the wind speed, and the intensity of the width from this will give the intensity that we call this SNR, which is how much intense is the backscattered or turbulence layer, or we can give the width of this. The echo will give the turbulent, but that's the other one. How much turbulent is the atmosphere? So huge information is buried in this one single backscattered echo, and like this we'll get almost like near surface to 21 kilometer using this MST radar. So typically we'll measure, as I mentioned, in the three half, one in vertical and other two in the half vertical, either in east west or not so. And we simply there are some few equations which we can derive the zonal and meridional component of the atmosphere, including vertical. A typical example is shown here, like a zonal wind right from surface to almost 22 kilometer, meridional wind here, and vertical wind here. You can see these two information, zonal and meridional wind, we can get from the radar sondes also, but this vertical wind is the unique parameter which will get from the Indian MST radar type of radars. And using all this information, we have investigated several atmospheric processes that includes winds and waves like tides, gravity waves, and equatorial waves. So, for example, gravity waves have the periods right from 30 minutes to from the blind first frequency to almost like initial period. So to sense this, then there is no other technique. In fact, the radio sounders we cannot launch very frequently, and we need to depend upon instruments like these radars. And the turbulence is another important parameter which gives by these, which will sense from these radars. And the amount of energy being carried from these gravity waves from the terms of momentum flux will be estimating from this radar. And the troposphere dynamics, which is also very important, that particularly utilize the stratospheric troposphere exchange process, is very important to understand the weather and climate. And it has become very important role in knowing even in the tropospheric weather. And also we will be because we can sense all the three-dimensional components of the winds. We can use this technique for the monsoon dynamics and also to understand part of the circulation, particularly Hadley circulation or ITCZ movement. All these things we can get it from these radars. And though these are all called clear radars, but we can get some information on the precipitation or convection. And we will be particularly from 60 to 80 kilometer or 70 to 90 kilometer, we'll get a lot of information on mesospheric dynamics, and also we'll get very good information on ionospheric irregularities. A typical example is shown here from shown in the January to December, all the three components. You can see the tropical jet, particularly during the monsoon season, which is persist around the tropos altitude. And you can see that the vertical wind always upward in the upper troposphere. And these are all very, very important for understanding the stratospheric exchange process. So, but this information, I am showing one of the typical example how the information and part of the circulation we can get from the single station itself. Here you can see in the figure, you can show, and in fact there are several circulations that exist. As I mentioned, the Hadley circulation or river Doppler circulation, and by putting this kind of radars at single location, we can get the part of this circulation. Where a typical reverse Hadley circulation is shown in this kind of example. We got from the Indian Hemisphere radar, average from 96 to 2012. You can see that the monsoon winds, the easterly jet and low level jet here, and it's a westward and southward and downward. This gives the part of this circulation. Suppose if you have this kind of radars well distributed, and a new current, there are almost like 5 ST or MST radar setup has come in India, and is a part. And thanks to DST for sponsoring these radars in India. And one is located at Cochin, and another is Gadanki, and another is in Gahuti, another is Nainital and Harimghata, Calcutta. It's in Calcutta. So if we use this kind of network of radars, we can get the several atmospheric processes, particularly the monsoon dynamics and circulation, and wave dynamics and coupling, and also the ionospheric research. These are all network of radars are very, very important, becoming very important. And as I mentioned in my first slide, to get more information about the 70 to 80 kilometers above, there are some of the network like we have the Gadanki MST radar and Tirupati SV Meteor radar, and also Tumba, Tirunelveli we have, and Kolhapur MF radar we have, and this kind of networks we are using to get the information for the middle atmospheric or upper atmospheric research. Now, but these radars are a very big gap exists from 22 kilometers to almost like 60 kilometers. We cannot get any information in this region using this observation, because as I mentioned, the basic backscatter is basically from the refractive index fluctuation due to temperature, water vapor in the troposphere, lower stratosphere, and whereas in the electron density in the mesosphere. So we'll get some information. You can see that this is the mesospheric echoes we got in the typical day from the Indian MSC radar, and these are very nice echoes we'll get in the lower atmosphere. But you can see there is a big gap. So to fill this gap, we basically use the optical instruments like the Rayleigh lidar, which I'll be touching upon the next slide. And to get more information on the middle and upper atmosphere, we use Meteor and HF radar, which I'll not be covering in this thing. Now, going to the optical techniques, where there is a big gap to understanding, particularly the temperatures between or any information between 20 to 60 kilometers, we basically depend upon the Rayleigh lidar. But there are several different types of lidars are available similar to the radar, where we have low Ratnam wind profiler, MST radar, SD radars for covering up to 20-22 kilometers. And we have got a Meteor radar or MF radar, which will go to upper atmosphere like that. In the optical technique also, we have several types of lidars. And basically, this depends upon the atmosphere molecules or gases present in the atmosphere. This can be sensed using the optical techniques. And I'll not touch upon more details upon how the backscatter is being measured in my scattering and Rayleigh scattering, and what information we are getting. But there are different types of lidars are available for getting different information. For example, boundary lidar will give the aerosol extinction profile, information of boundary layer altitude, cloud base height, and optical thickness of both clouds and aerosol. And main lidar basically for tropospheric aerosol and cirrus cloud, it can go up even up to 20 kilometers, but boundary layer are restricted to maximum 8 kilometer altitude. And Raman lidar are widely used for the water vapor and temperature getting information. And as I mentioned, to get the information on the stratospheric and mesospheric temperatures, right from 30 to 90 kilometer, we basically use the Rayleigh lidar. And these, as I mentioned, these radars have a very big blank of from 20 kilometers onwards to 60 kilometers. And part of those winds can be covered using the Rayleigh Doppler lidar technique, where it gives information on the winds from 15 to 45 kilometer altitude. But it's not that much high good temporal resolution, but we will get very good information. In absence of any information, this plays an important role for getting information from 15 to 45 kilometer. And we also use the resonance lidar to get the sodium densities from the middle and upper atmosphere. And as I mentioned, for getting the ozone information, very high temporal resolution, vertical resolution, we also have differential absorption lidar. So these are some different types of lidars available to get the information on aerosol, cloud, and temperature and winds. And a typical examples of these lidars we have at Gadanki is shown in this slide, where wide varieties of lidars exist, and they're all mostly are operational from our side. And some of the lidars, I have more than 2 decades of observations, particularly from the ME and Rayleigh lidar from Gadanki. Now, what basically it gives is a typical example as round-the-clock observations from 0 to 23 kilometer. You can see from 0 to 20 kilometer altitude and round-the-clock observation. You can see a lot of huge information is buried from these backscattered returns from these lidar observations. You can see that boundary altitude, evolution of the boundary altitude. You can see from below the 2 kilometer, how in the daytime and nighttime it is getting modulated in from the backscattered ratio. We can get all this information from the boundary altitude. And that whenever there is a thick cloud, you can see that the signals are not penetrating this one, but we'll get a very good information on the cloud base and thickness of the optical thickness of this cloud. And when the cloud is, when the weather is clear, you can get a very cirrus, a thin transparent cirrus cloud present in the Utilis region. We can get very good information on this info from this kind of lidar. A huge information is buried from this lidar, and we can get several atmospheric parameters like aerosol extinction profile, boundary layer light, cloud base height, and optical thickness we can get. And also we will use these lidars for deriving the temperature profile. As I mentioned, particularly the Rayleigh scattering will give the information on the temperature in from almost like 30 to 100 kilometers or 80-90 kilometers. A typical example is shown here. And I'll not go much details about the basic technique, but I'll let you know what are the literature from where you can get more information on these techniques. But as I mentioned, all these radars or lidars or in situ measurement, they're all point observation. Wherever that observations are there, we'll get. But if you put these kind of instruments in the satellite, what picture we are giving, this slide tells about that. That we all know that Calypso launched in 2006 is very good. The first time a lidar being flown in the satellite, and it's going to give the picture like this, which I mentioned in the previous slide, that boundary altitude, the boundary layer aerosols, clouds or cirrus clouds. You can see when the overpassing of that satellite at a given position, latitude and longitude, you'll get huge information on this one. So in a period of 16 days, you can get all this information covering complete globe. So such a nice information we'll get from these kind of sensors, which when we keep in the satellites. But getting the winds from the satellites are so far, there are no other techniques except using again from the optical techniques. For the first time, European Space Agency has launched a mission called ELIOS, and this is the first space-based Doppler wind lidar, which is launched on 22nd August 2018, and it gives the wind information almost covering the tropospheric altitude between surface to 20-25 kilometer and with vertical resolution of 0.25 to 2 kilometer, and a very good instrument and first of its kind. And some of you, if you are interested to use this information for for knowing the winds particularly, and simultaneously aerosol and clouds, this is the first best example set by European Space Agency, which give huge information using the optical techniques. Now, and there are some other optical techniques available for the middle atmospheric research, particularly that we call as air glow. And we have three types of air glow. One is the OH or O2 or O1S. And this is typical typical altitude is mentioned here, 87 kilometer, 93 and 97. And we have another at 220 kilometers altitude also. Basically, that you can see that the fringes, the light and dark backgrounds are moving in this movie. And this gives a huge information is buried in this information. And this gives a very good information. Particularly, we can also derive the temperatures using these instruments. And we can understand the middle and upper atmospheric coupling. Particularly, this instrument plays a very important role. Now, coming to the summary, I have covered several techniques, particularly which is emerging in recent days for atmospheric probing. And of course, I have not covered anything related to trace gases or radiation. And it has its own way. I think when the lecture series of aerosols comes at that time, those instruments can be introduced. And so far, I mentioned the standard instruments which are available for most of the quantities, like meteorological parameter surface, I have covered almost. And in situ measurements, I covered little more. And the new emerging techniques like cobalt, CPS, ozone sondes are nicely covered in this talk. And we will get more accurate information from these kind of in situ observations. And it has become very common nowadays for getting your trace gas or clouds or aerosol information. Now these have been used. And most emerging techniques is like drones or UAVs have become very common for atmospheric probing. And several field campaigns have been conducted so far for understanding the several atmospheric processes, particularly related to the trace gases and aerosols. And nowadays, superpressure balloons flying at a fixed altitude to cover a globe in few days has become very popular. And almost like 2019 to 2025, these campaigns are planned. And huge information we are going to get, which is unattempted so far. And those information we are going to get from superpressure balloon. And the high altitude aircraft campaigns have also become very common nowadays. And I slightly covered the radio and optical techniques for probing the atmosphere, particularly the radars and lidars I covered. And to some extent, those lidar technique which is installed in the satellites like Calypso or Alias instrument I covered. And I have not touched any other satellite remote sensing for middle and upper atmospheric research. And it demands a separate lecture on the satellite remote sensing, because it's very difficult to cover huge information which we are getting from the satellite and different techniques and different platforms available for the satellite remote sensing. And please note that here whatever covered is the techniques are only indicative and but not exhaustive. And for some of the instruments which I mentioned, which I used in this presentation, you can get more details by visiting our site, that is www.nal.gov.in. And you'll get, and some of the data sets are also available, which are freely accessible, and you have to, few data sets are freely accessible. And suppose if you want to get any specific data set, you can write to us, and how to reach us is also mentioned in this site. And before I conclude my presentation, I should remember a PAM atmosphere scientist of India in general, and middle and upper atmospheric and aerosol radiation research in particular, Professor V. Krishnamurthy, who I had a long association with him, and he's a pioneer in some of these techniques which I mentioned. And he has several things he has introduced in India, and I'm so privileged to work with him. And jointly we have published one textbook called Terrestrial Atmosphere and Ionosphere, Physics and Experimental Techniques. And most of the techniques, the physics behind these techniques, is nicely covered in this book. And I suggest the early career students or MSc to go through some of the basic concept which we elucidated in this prestigious book. So with this, I thank SAMA for giving opportunity to present in front of you. And thank you very much. And I'm happy to take some of your question, answers, or clarifications. Thank you.
Thank you, Ratnam sir, for giving the very illustrative talk. Of course, this talk is on high demand because it's all about the techniques and observations. There are many questions we see. Now I request the moderators for the question and answers, Dr. Swagata and Dr. Kalpana, to take questions. and take to the notice of the panelists so that you can answer, you can respond to their queries. Swagata and Kalpana, over to you.
Yeah,
Okay.
thank you, Dr. Lakshmi. And Madam Kalpana ma'am, if you
Yes, sir.
I mean, you please mention the name, who is asking the question.
Can I unshare my slides?
Yeah, that is better. You can stop sharing.
yeah, you stop.
So, one of the anonymous attendee has raised a question that can we measure vertical temperature profile using radar or solar same as wind profile?
Yes. In fact, you can go through the Revati et al. 1996 paper, where they have shown the Brent-Weissler frequency measured from the radar can be used to get the temperature profile. It is possible, but that will work only under the clear sky conditions, not under disturbed conditions.
Okay. Okay, sir. Thank you, sir. Can we take the next question?
Yes.
Okay, sir. One of the participant, Mr. K. Karthik, he is with the question that what are the satellite data gives information about thermal properties of the land surface?
You can use the Landsat.
Landsat, okay.
Yes.
Okay, so I think Mr. Karthik is listening to the answer of his question. Now, next question is from KB George, and he wants to get the answer of a question that in one of the slides as shared by you, sir, in one of the slide, RH profile shows 150% relative humidity at higher altitude. What conditions has made this possible?
Very good notice. Though I was rushing on the slides, very good. You have noticed nicely. Please note that relative humidity is calculated over the ice, not over the water.
Is that okay, sir?
Yes.
Okay. Now, thank you for this question, sir. Next question is from Bhumiraj K. And he wants the answer of his question as how to measure biogenic aerosols.
In fact, I'm not the expert in that field. Maybe when it is covered by other experts, they will cover in that.
Okay. Okay, thank you, sir. Mr. Bhumiraj, you will get it from the other expert lectures for the answer that you are searching for. And then one of the candidate, that is Vamba Chinda Claudine. There is a question that in the equation in slide 9 of the relative humidity, he wants the explanation more on that equation in slide 9.
I suggest you please go through that book or the reference which I given in the slide. It can tell us all the details.
Okay. Okay, sir. Now the next question is from the Paparao, and he wants the answer regarding the stratospheric warming and how it affects the air pollution and future climate change.
Stratospheric warming?
Stratospheric warming and how it affects the air pollution and future climatic changes depending upon that.
As far I know, tropospheric warming and stratospheric cooling, but I never come across stratospheric warming.
So maybe it is due to sudden stratospheric warming.
Oh, you are talking about those stratospheric warming. Okay.
Sudden stratospheric warming. Maybe that he might.
So these are all actually the high altitude phenomena, but those effects can be seen even in the tropical latitudes. And but that is don't treat them as a stratospheric warming. Stratospheric warming has a different meaning.
Yes, sir. That is sudden stratospheric warming.
Yes.
Referring to.
Yes.
Okay. Thank you, sir, for this question from Papara. And the next question is from Dr. Rajendra Kumar Panda. And he wants the answer that, can you highlight some matter about the volatile organic compound measurement in the atmosphere?
As I mentioned very clearly, that aerosol and trace gas part has been not covered in this talk, and a dedicated talk is being planned when that aerosol talk comes.
Okay. Is
Maybe Swagata, you also can pick a few questions, maybe from YouTube and
Okay, yeah, there is one question, ma'am. Thank you, ma'am.
okay,
And
sir. Thank you.
yeah, so is there any instrument or devices that can be used to detect or track cumulonimbus cloud formation, movement, and evolution? Asked by Mohammad Saizman Faisal. Is there any
See-
instrument or devices that can be used to detect
See,
or track cumulonimbus? Yeah.
the clouds can be detected both ground-based and satellite remote sensing. But to know about what type of cloud, and we need a little more. You need to follow a little more thing. But of course, depending upon the cloud properties, one can say the cumulus or non-cumulus cloud. But per se, a separate technique is not available to get the information on cumulus nimbus or cumulonimbus clouds. In general, cloud information we get it.
Okay, sir. So there is another question already answered by Professor Shamsardar. But still, is there any instrument to measure the hydrometeors present in convective clouds?
You see, all these techniques, most of the techniques which I covered, they are very good in the calm period. In the disturbed period, in fact, because those are based upon those equations which will work in the calm period. Anything which is in the disturbed period, several of those assumptions will not be valid. So in the disturbed weather condition, it's very difficult to get information on those hygrometers.
maybe satellites can measure, right?
No,
Hydrometers.
but those are also in the normal condition is fine. I mean, in the disturbed weather condition, whatever the assumptions we are making will not be valid.
Okay, so I think there are. Is there any more questions? For which satellite is being used for taking data from AWS? Is not the exact question.
There are many more questions. I see.
Yeah, which approach is best for calculating
Yeah.
boundary layer height in tropics?
There is no single answer for that. For example, boundary altitude is indirectly measured, whatever the technique. For example, if you use the LiDAR as the technique, it's basically backscattered from the aerosol or cloud at the near the boundary layer altitude, whenever there is an inversion, or it will be more information, more concentration will get either in aerosol or cloud. So suppose if there is no scatterer, no aerosol or no cloud, so it's not possible to get the boundary altitude from the LiDAR. The same with the radio sonde also. Basically, we use the potential temperature or Vasho potential temperature or gradient in the water vapor or temperature directly. We use to get, but any of these techniques will not be valid at all the times. So there is no single technique to get the boundary information. Caution is advised when we are using for any of this information, restricted to that instrument, that parameter only. But if you want to compare, for example, radio sonde, radar, LiDAR, if you keep aside, side by side, and if you want to calculate the boundary altitude for respective boundary altitudes given from those backscattered echoes or backscattered photon counts, so we will be missing some of the information because all the atmospheric parameter will not behave same in the different parameters.
Okay, sir. And is there any, what is the difference between boundary layer height and mixing height while we measure from the satellite?
Boundary layer definition, if you go to the STUL book, you will get more information on that. In fact, boundary layer altitude has several definitions. For example, it includes stable layer, capping inversion, mixed layer. So in the daytime, that we call as a convective boundary layer or mixing layer, which is well mixed because of solar insolation. In the nighttime, because such mixing is not there, we call a stable boundary layer. So basically, the mixing layer comes in the daytime phenomena of the boundary layer. Is one of the boundary layer concept.
Okay, sir. And please give a clarification and complementarity between radar and surface observation.
Pardon me?
What is, I think the exact question is that please give a clarification and complementarity between radar and surface observations.
See, surface observations, mostly they're in situ because it is sensing the atmosphere, the immediate atmosphere, which is where the sensor is placed. And therefore, if we radar without touching, or in fact, both passive and active radars are there, but without sending that instrument into the atmosphere, we'll get information that is called radar.
I think, okay, why KI used in ozonosphere data? Any other chemical can we use?
See, radar definition, if you go to the STUL book, you will get more information on that. In fact, boundary layer altitude is one of the boundary layer concept.
Any other chemical can we use?
As I mentioned, there are 3 different types of ozone sondes. In the electrochemical cell type of ozone sonde, basically there are cathode and anode solution, and so we will get the difference between the background current and the current being measured when the ozone is being transmitted through the from the air. So that is the concept in the ECC ozone sonde. But other 2 types of sondes are there where they don't use at all this rotation method.
Thanks a lot, sir. I think Dr. Lakshmi, we can.
So there is one more question.
Okay.
Hello, sir. He is from Anurag. He's from CURAJ. Hello, sir. Thank you very much for a nice talk. I have a question. As we know, water vapor is the most influential greenhouse. Why? Can you please brief about this? A master student, I hope.
In fact, not only water vapor, there are several parameters. Particularly the CO2 is more important. Then again, methane is also more important. So first you have to understand what is the, that is the only, coming to the water vapor, it is the only parameter where it can be translated both from solid, liquid to gaseous. So any change between these phases or because of any change in the background will be affecting these changes, and from the transition from one phase to other phase, there are several things will be happening. So basically this water vapor, in fact, I'm just telling in the general sense, but if that is the dipole moment, you can, there are several other criteria you can see why the water vapor is more important greenhouse than compared to other things.
Yeah, so there is one more question I can see. Is it possible to forecast large-scale cumulonimbus landfall accurately 3 days ahead?
I'm not expert in that field.
Yeah, that's why I didn't ask. Yeah. The question is, there are 2-3 questions, just little outside, but if you want, when I can put those questions like why ozone concentration is more at poles. It is not exactly the instrumentation question. So that's why I skipped it.
No,
but
in fact, I have already mentioned with a slide there, though ozone is being produced more in the equatorial latitude, because of the brevet adoption circulation, the air from the tropical latitudes will be lifted to and transported to the polar latitude. That is the reason we will see the more ozone concentration there.
Okay, that's all.
Yeah, I think. Yeah. Ma'am, Kalpana, ma'am, do you have more questions?
Sir, one question I can see from Dr. Devya Prakash, and he is saying, I think sir has answered this question, but I'm out of confusion putting this question. How to get the mixing height through satellite? Is this question answered?
I have marked with boundary layer height that question.
Okay.
Yeah, but still you can ask. Yeah.
See, the satellite, satellite per se, they cannot give the mixing layer altitude specifically. Depending upon the time of the measurement, you can assign. For example, if it is the daytime, it is at convex boundary layer. If it is a nighttime, stable boundary layer. And the difference, for example, in the daytime, it will boundary layer between 1.5 to 2 kilometer, 2.5 kilometer. But stable boundary layer will close to 500 meters to 1 kilometer, less than 1 kilometer. So depending upon the time of the observation, you can assign that as one of the type of the boundary layer. But per se mixing layer, you cannot identify from the satellite.
Okay. And one more question is, there's which type of middle atmospheric data used for forecasting of surface weather? From Dimant Kumar Bagasia.
See, there is no direct data which we use from the stratosphere or middle atmosphere to forecast the troposphere. In fact, there are several atmospheric phenomena. Any disturbance in the lower stratosphere can perturb the tropospheric weather and climate. But per se, a single parameter will not influence the tropospheric weather or climate.
Okay.
See, for example, the exchange between stratosphere to troposphere, that ozone exchange, particularly in the ST exchange process, that will affect the temperatures in the upper troposphere. That can change the circulation features. That can affect the several atmospheric process. It is one way of looking at.
Okay, sir. Thank you, sir. And the next question is from Dr. Narendra Kumar Parik, and he's asking that which satellite is being used for taking data from AWS, Automatic Weather Station.
Can you repeat?
Which satellite is being used for taking data from Automatic Weather Station?
I think question is wrong.
Yeah.
So
Maybe his meaning is that which satellite can measure the parameters of what AWS can give.
parametric value he needs.
Yeah, probably.
If that is a question, see satellites to some extent, whatever the information we are getting from temperature or any other information from the satellite, they are not valid up to the surface. Only 1 kilometer above or 2 kilometer or 2 kilometer above, for example, temperature to some extent, and even the aerosols what we measure from the satellites, they are not that accurate from the up to the surface. From 0.5 kilometer or 0.75 kilometer generally will take, because several other processes will be happening and several other corrections will be involved in the satellite retrieval. So we cannot correct all those things to get information what automatic weather station is giving. In fact, automatic weather station will give like temperature, relativity, wind speed, wind direction. It's very difficult to get from the satellite at that surface level. For example, but rain to some extent we can get.
What he means is that lots of AWS all over India installed by IMD, and those data from the AWS are accessed through satellite and then relate to the ground station. So is that what he means, that which satellite is used to relay retrieve the AWS data and relay back to the stations?
All those ground data we need for the ground truth validation purpose.
So the validation, his question is that how the AWS data is used to satellite, something like that. So what I can interpret is that what he's asking, which satellite is used to access the AWS all over India, and then relate back to the Earth station.
He can elaborate his question and mail to SAMA email so that some of the experts may reply that email.
Yeah, there are 2 more questions now. Should we?
Yeah, I think we have another 2 to 3 minutes. Probably we can spend. So you can take 1 or 2 questions.
Yeah. If sound wave is to be used for measuring vertical temperature, should sound wave reach 3 kilometer altitude? If so, is it reaches to 3 kilometer? If so, the sound must be very sharp and can harm our ears. Is it so?
No. See, actually there are some specific instruments available like SODAR or RAS, radio acoustic sounding system, or sound navigation. It is called SODAR, sound detection and ranging. So these things, it definitely it may not be harming our ear, but there are some specific frequencies in the sound waves which we can allow to propagate. And for example, in the RAS, the sound will be transmitted, and with the radar, at wherever they interact with us at a constant. I don't know exactly what is the principle in that, but using the radio sounding system, we'll get the information on the temperature covering up to tropopause altitude using sound waves.
Is there any instrument for measuring soil moisture? Yes, it is there. So what is the name of that instrument?
I don't know exactly.
There is no direct measurements. I think you can measure the soil temperature, and proxy you can make, like if it's satellite, you can use brightness temperature data. But that albedo is become very problematic. Soil moisture, there is direct measurement is difficult.
So there is an institute in Jodhpur. There is an institute. I don't remember exact name. Radio something, which is used to retrieve the soil moisture. You can find out from the internet the exact name of the institute.
No, that soil moisture nowadays people are using the radio reflectometry.
GNSS.
GNSS reflectometry. That is popularly used to be for measuring the soil moisture.
Yes. So mostly there is no direct measurement of soil moisture. Only probes. People are using the probes. Yes.
I think all the question is answered. Only 1 question left. So let's finish with that question. Can we measure CO2, NOx, and SOx over certain area by satellite?
Over?
Can we measure carbon dioxide, NOx, and sulfur dioxide over certain area by satellite?
I think there are some dedicated satellites. For example, if you take the AIRS, they'll give the profiles of carbon dioxide, to some extent SO2, but I do not know exactly about NOx. Maybe that Senthil, that OMI will give the NO2.
I think Rohini, you can.
Yeah, Senthil sir has already answered. Senthil can do this. And Aries is giving socks and
Yes.
Okay, I hope all the questions have
yeah.
been answered.
Yes.
I think this is the first lecture where we answered all the questions mostly. So thank you very much, and thank you to the panelists. Is very, what I can say, precise to the question and very precise to giving the answer also. So thank you very much, sir. So I think we have come to the end of the session. Before just closing it formally, we request Dr. Mohan to deliver the vote of thanks. And before that, we panelists requested to turn on their video for a photograph. Please, thank you.
Tyagi sir, please.
Mohan, you are taking?
Yes, I am also taking.
Yeah.
Just a minute. Tyagi sir, video is not switched on yet. Just a minute. One more. Done.
Thank you.
Oh, Tyagi, okay, 1 minute. Sir, video is switched on now. Thank you, sir.
Yeah, Mohan,
Done.
please, a vote of thanks.
Yes, please. Yes. Good afternoon, everyone. It is my great honor and privilege for me to present the vote of thanks for today's International Lecture Series session. On behalf of the participants and SAMA, I am very much glad to express my vote of thanks in this session. First and foremost, I would like to heartfully thank our today's resource persons, Dr. M. Venkat, Ratnam, head of the Aerosol and Trace Gases Group, ARTG of NARL, National Atmospheric and Research Laboratory, Gadanki, India, for being here with us and for the excellent delivery. I was listening to your speech with keen interest, and I believe all other participants did the same and enjoyed it most. I am confident and hopeful enough that your sharing of knowledge, experience, and views with us on emerging techniques in atmospheric observations gave us new ideas for thinking and challenges and would encourage us to work in this sector in future. Our heartfelt gratitude goes to the respected member of the Coordination Committee of SAMA's training course, SRM-IST, especially warm thanks to Professor Air Vice Marshal retired Dr. Tyagi sir, President of SAMA, Professor Dr. Someshwar Das sir, Secretary General of SAMA, Professor Dr. Sharad Premalal, former Director General of Meteorology of Sri Lankan Meteorological Department, and he is also the advisory panel member of SAMA. Professor Dr. Dotla Venkata Bhaskar Rao sir, Dr. T.V. Lakshmi Kumar from SRM IST, and also he is the session moderator of this international lecture series. Dr. Rohini Bhawar, SPPU India, Dr. Kalpana Patel, SRM IST, NCR India, Dr. Swagata Paira, BIT Mesra, and also Treasurer of SAMA, and Board of Directors and Organizing Committee for arranging such an effective, excellent training program. I believe this program has become a fruitful and supportive one in changing the knowledge, skill, and attitude of the participants to a better level. Finally, I would like to thank the member of SAMA and all the participants from the South Asian Meteorological Association member countries and also abroad of 9 countries as well, and their spontaneous interaction for making the program live, enjoyable, and memorable. Thank you all once again for being here with us. Thank you, sir.
Thank you, Dr. Mohan. And I thank all the panelists on behalf of SAMA and SRM-IST for being with us. I think with this talk, we have completed the orientation talks of this module. From next week onwards, we'll be having the actual textbook topics. So to start with, we'll be having next week, we have 4 weeks module on atmospheric radiation. The speaker is Professor D.V. Bhaskar Rao. Bhaskar Rao, sir.
Thermodynamics, I think. That is atmospheric thermodynamics.
Atmospheric physics.
Sorry, atmospheric. The module is atmospheric physics, and first module we are going to have an atmospheric thermodynamics. So the 4 lectures will be 4 weeks will be delivered by Professor D.V. Bhaskar Rao, Andhra University, Visakhapatnam. So fortunately, he is with us today. Anyway, we will formally introduce you, sir, next week. So I request all the participants to attend these talks without any fail. So thank you very much once again. Thank you all panelists, and thank you my friends and colleagues. And once again, thank you very much all the participants for your patient hearing. Thank you very much. Next week we will be meeting as usual. So we will share this presentation with you soon in 1 or 2 days. Thank you. Thank you very much. I'll stop.
Thank you.